The Casimir effect, a quantum phenomenon believed to arise from vacuum fluctuations, manifests as an attractive force between uncharged conducting surfaces. While traditionally studied between parallel plates, recent research has extended this analysis to more complex geometries, including concentric square cylinders. The Casimir torque between two concentric cylinders was investigated using the multiple scattering method. This approach considers the material properties of the cylinders and their interaction with the quantum field, offering insight into the magnitude and direction of the resulting torque under various conditions. The study revealed two stable configurations, one at a 0-degree alignment and another at 45 degrees. A torque is generated whenever the rotor is not in one of these stable states, causing it to rotate until it reaches equilibrium. If the rotor is positioned at an angle less than 45 degrees, it rotates counterclockwise toward the 0-degree position. If it is positioned beyond 45 degrees, it rotates clockwise toward the 90-degree position. To further support the theoretical predictions for concentric square cylinders, we employed a water wave analog system, an experimental method originally developed by DiNardo et al. In 2009. In the classic setup, two rigid plates are vertically suspended in a vibrating liquid bath. The induced surface waves exhibit reduced amplitude between the plates, causing them to move closer, mimicking Casimir attraction. For the concentric square cylinder configuration, we used a similar approach with two methods of wave generation. In both setups, a rigid square frame was mounted on a metal sheet, with a central axle fixed in place. A square rotor was placed on this axle, and water was added until the rotor floated freely. For the first method, a speaker-driven shaft moves the rotor vertically, generating surface waves. For the second method, a speaker placed beneath the liquid tank generated waves through acoustic vibration. Both methods produced consistent results. Two stable configurations emerged. One where the walls of the rotor aligned parallel with the outer square boundary, and another where the rotor's corners aligned as closely as possible with the outer square's walls. These results closely matched the theoretical predictions. Experimental observations confirmed the presence of Casimir-like torques in this macroscopic analog system, validating the theoretical model. The arrangement also demonstrates the utility of water wave analogs for exploring Casimir effects beyond the standard parallel plate configuration. Understanding Casimir torques in complex geometries has important implications for nanoscale device design, where these forces can influence mechanical stability and performance. Water wave analogs offer a tangible way to investigate such quantum phenomena, helping bridge the gap between theory and experiment. Additionally, these analog systems may pave the way for devices with engineered stability behavior, including those with a specific number of equilibrium points, or even none at all. We are currently researching and prototyping devices that theoretically exhibit no intrinsic stable configuration. Developing such a system could be revolutionary for our understanding of Casimir forces and zero-point energy. Subscribe for updates as we continue exploring these exciting frontiers.